Alright, so let's look at this idea of what locking is. So this is another way things can go wrong when you do simulations. And this is related, what we're looking at is really related only to the Q4 element, the quadrilateral 4 element. And there are two ways things can go wrong when it comes to locking, typically in the linear elastic scenario. And the one is called shear locking, and the other one is called volumetric locking. And both of these occur when you have the bending mode induced on that element. Okay, so to illustrate this and to show you how things can go wrong, what I'm going to do is I'm going to take a beam of a 10mm long beam, 0.5mm high, 1mm thickness. Okay, so that's essentially what we have, and we're going to model it with a bending with a moment of 5 Nm. That we're going to apply at the right hand edge. Okay, so that is essentially the loading that we apply to the edge. The left hand edge is supported by rollers in vertical, and there's one X displacement that's restricted from moving. Okay, so that is what we have. So there's no rigid body motions, it's just pure bending moment. So we expect to see with this only a moment applied sigma xx stress, because we're applying it at that edge along the length of the beam. That edge is perpendicular to along the length of the beam on the right hand side. So that's what we do. So if I can illustrate it here, we're essentially applying a moment here of 5 Nm. Top we can see is nice in compression, bottom nice in tension, and that's the problem that we're dealing with. Okay, we expect to see only sigma xx stress, sigma yy should be 0, and sigma xy should be 0. A pure bending moment, there's no shear involved in this problem. Okay, here I've calculated just quickly for you what is the expected megapascal solution that we're supposed to see. Maximum sigma xx is supposed to be 120. Okay, let's run it. What I'm going to do now is I'm going to show you the Q element does not have this issue. So I'm going to run one Q element, Q8, sorry, not the Q element, the Q8 element doesn't have this issue. I'm going to show you with one Q8 element. Okay, this is what this 1 by 1 means. The first index here is the number of elements through the height. Second index, the number of elements along the length. One Q8 element, let's see what happens. We expect to see maximum sigma xx of 120. Okay, so let's see what we get. Displacement, you can see that's the type of displacement that we see. This is mitigation factor of 10. Full integration. You can see here von Mises stress. Maximum is 120. It seems like it's everywhere 120, but as a matter of fact, it's because we essentially plotting only the stress at the coordinates. That's why it looks like it's 120, but it will be varying linearly. It will be varying down to 0 to the model. So that's essentially what you would see there. Sigma xx, you can see a better idea because now we see compression and tension as expected. Okay, 120, spot on. You see this is inexact. So what I want to show you is with one Q8 element, I can model a pure bending problem exact. Okay, this is not an approximation or anything. This is exact. Look at sigma yy 0, sigma xy 0. No shear, nothing weird going on. Exact solution. Let's see if what we do is we change from the Q8 to the Q4 element and see what happens. So now I'm going to model this a Q4 element. And let's use 3 by 3. 3 elements through the height, 3 along the length. And let's see what we get out as an answer. Magnification factor is also 10. So we expect to see a displacement like we saw with the Q8 around this, because we know this is now our exact solution. Let's see what we get out. Sorry, this is wrong. This is this one. Look at the magnification factor of 10. Look at the displacement, amplified displacement. You see, significantly different. Okay. Von Mises, 30. Okay, so it's a 30 that we have here. Sigma xx, it's supposed to be 120, 6.87. And I'm using 3 by 3 elements just for a pure bending. This is one of the simplest problems we can model. Pure bending moment, 3 by 3. Look at how the things go haywire here. Sigma yy, 0.733. Also, things are going haywire. Supposed to be 0. Sigma xy significantly larger. So this is at least quite low for sigma yy, but look at the sigma xy, 17. Much more than what we have as the normal stress. So it's twice that. So our shear is twice the amount that we have for our normal stress. Okay, and we're already using 9 elements to model this. It's not like we're not using any elements. And this is important to understand. We're inducing bending moment on the Q4 element. Now we have issues. Okay, so hopefully by the end of this notebook, I would have convinced you that if you want to model with finite elements, use Q8 elements, use 20 noded brick elements, avoid the Q4 elements for 2D or the 8 noded brick elements for 3D. Rather just use these quadratic elements, especially if you use different finite element packages and you're not sure whether they've tried to alleviate some of these issues by doing some fancy tricks. Okay, so but this is just to show you, this is out of the box a Q4 element, the response. Okay, that we would get. Now we're going to go and say, let's model it again, but let's say 1 element through the height, 9 along the length. So I'm using 9 elements along the length. Let's see what we get now. Magnification factor, significantly more displacement. Can you see that? Significantly more. Now the hormesis is up to 70. Sigma XX, luckily, is at least up to 44, thereabouts. Still tension, compression, as we expected. Sigma YY also significantly 13. And Sigma XY 34. Let's look at those values. Sigma XY is now for the first time at least under the Sigma XX, but it's still very large. And so the hormesis that we see here, that is up to 70, is mostly made up of the shear contributions. Or largely, it's a large contribution from the shear and from the Sigma YY. It's not only thing that's coming from the Sigma XX. Okay. So that is sort of using 9 elements along the length. For just the pure bending, I mean, this is, what I'm doing is I'm saying 9 elements like this, 1, 2, 3, 4, 5, up to 9. This is how we're breaking up this structure, and we have issues. Alright, so let's see what happens if we go the other scenario where we say we've got 9 by 1. Okay, 9 elements along the height. So I'm going to break it up like 1, 2, 3, 4, 5 with these long elements like this. Let's see what happens now. And if we do that, almost no displacement. Also magnification factor of 10. Look at that displacement, almost nothing. Von Mises is 10. Sigma XX is under 1 megapascal. Sigma YY is 1 order less than that. And Sigma XY is up to 7 megapascal, 7 times larger than Sigma XX, and it's supposed to be 0. Okay, Sigma XY is supposed to be 0. It's sorry, 6 times larger. No, 7, 6 times larger than what the well, more. Yeah, it's more than 7. So it's maybe about 9 times larger than Sigma XX, because it's, I thought it was about 1, but it's about 0.8. So that's quite a significant jump that we see here, a difference here. Okay, and this is just to show you. I mean, we are modeling a problem in pure bending, nice rectangular structure in pure bending, and what I'm showing you here is we are way off of the 120 MPa for Sigma XX. Okay, way off. And this is how easily things can go wrong using the finite method. Again, if we don't do FEM, if you don't verify. That's as simple as that. We don't do FEM, we don't verify. And the go-to message from this, so hopefully, is that from just looking at this for now, is that we better maybe stick to stuff like Q8 and Q20, the 20 noded brick elements in the beginning when we start modeling with finite elements, so we avoid a lot of these potential issues. Okay, this is hopefully giving you an idea how simply things can go wrong. What we can try and do is to use reduced integration of the Q4 element to try and alleviate things. So I'm going to do the reduced integration now, and let me just show you the magnification factor at 10 on purpose, so you can see the craziness we see. This is going back to the Q4 3x3 element. If I try to use reduced integration to alleviate things, look at that. That's again a communicable mode that kicked in. So if I make it 1e minus 9, at least I start seeing stuff like this. But look at that, hormesis stress 10 to the 15. So our one attempt to try and alleviate things is maybe to try and use reduced integration, and that's made things a lot worse. Okay, so that's not gonna work. Okay, so I can do the reduced integration on the 1 by 9 element. Okay, so 1 through the height, 9 along the length. Let's see what happens here. Magnification factor of 10, also craziness, 10 to the 17. You can just see this is not helping. Reduce integration on the 9x1 elements. So that's now, you can see those lines there. So let's see what's happening here. 9x1 element. The magnification factor is 1 in minus 6, and it already looks like this. 10 to the 13, 10 to the 12, 10 to the 13, 10 to the 10 for sigma xx. So this is not at all sensible. Okay, so this what is showing you is that the way if you want to alleviate issues with shear locking, what I'm advocating, what I'm trying to demonstrate to you is go back to your Q8 element. Here we can see the response for a single element, not 3 or 9, not 9 elements like we've seen with the Q4, and it's still a disaster. Just a single Q8 element can already do a pure bending solution. Okay, just be caution, this is for pure bending. As soon as shear is involved, this solution won't be exact anymore. It would also be an approximation, but it won't be flaunted with issues like the shear locking that I just demonstrated. Okay, so this concludes the idea of shear locking. The next video I'm going to do volumetric locking, which is another type of locking that can occur.